Hello, hi. Happy Sunday evening. Yeah, I took a long nap and just woke up. It's Sunday evening, so happy evening. Yeah, so I gotta correct something. In terms of the stress vector that we talked about a long time ago. Yeah, it's not exactly radial vector system. Okay, in radial vector system, you can rotate a vector and preserve the identity equality, right? That's radial vector system. But in when we calculate stress vector, you it's not equal. Okay, if two force is going squeezing in, yeah, you are doubling the stress, right? But if two vectors are in 90 degrees, it becomes this object start to move. So probably it's kind of equivalent to this square root of 2 diagonal vector pushing. Okay, so yeah, so in terms of stress vector, yeah, they're not equivalent. Okay, so you cannot just rotate and preserve equality. Okay, so that's that. Okay, yeah, I make mistakes sometimes. So please forgive me. I mean, I'm a human being too, so I make mistakes. Okay. Let's bring in the whiteboard and let's talk about things. I'm gonna bring back this chair with back support. Oh boy. Okay, so uh um so the discovery of brand new number, it's like, for example, like I squared is equal to -1. Okay, that's a very good example. This definition of this imaginary number, right? So basically, I is defined as a square root of -1. Okay, it's imaginary number, and turned out that this definition is very useful. Okay, whole this complex number system is something very very powerful and useful. Okay, yeah, the application in electronics and whatnot. Okay, and in terms of um, it's just expansion of this numbers. Okay, uh, so how about 1/0? Yeah, we can define it as a infinity. Okay, but the thing is this: this infinity is not exactly. It doesn't quite behave like numbers because it's a constant and also it's a variable. Like in physics, you have wave, right? I mean, light, light is both particle and also wave, electromagnetic wave, and also it's a photon. It has particular characteristic and also wave property as well, light. Okay. So yeah, this infinity, it's both constant and variable. Okay, analogous goes to light, having both properties of wave and particle. Okay. Yeah. So like the Gero Cantor, he tried to define this concept of infinity. You know what? Transfinite number or something like cardinality, ordinality. He used this Hebrew alphabet like Aleph, whatever. Okay. Um, I'm not sure why he chose to use Hebrew alphabet. Is he a Jew? I have no idea. Okay. Yeah. Anyways, this concept of infinity is being very useful. It's very useful in terms of this calculation of limit. Okay. To find whether this function converges or diverges. All right. Yeah. You know, like limit x goes to infinity. You know, 1/x is equal to 0. You know, and what's limit? Yeah, it's like what's the destination? Okay, where is this 1/x going? 1/x. You know, where at x, what is it approaching? Okay, 1/x. Yeah, x goes to infinity. 1/x is approaching 0. And it, yeah, but instead of writing this like limit x go to infinity 1/x, instead of doing that, we can shorten this whole notation as 1/infinity is equal to 0. Okay? Yeah. So we're gonna explore this limit a little bit, okay? Because it's very important in mathematics, okay? Yeah, forget about all this number system for now, all right? We need some room. So, yeah, infinity, that's very tricky concept, okay? Because, for example, let's say x minus x, and you have 2x minus x, limit x go to infinity, limit x go to infinity, okay? Here, this guy is equal to infinity, okay? But this guy is equal to 0, okay? But if x go to infinity, here's, you know, infinity minus infinity becoming 0. But here, x go to infinity, positive infinity, okay? 2x is infinity, infinity minus infinity is not equal to 0, okay? As you can see, twice of infinity is not equal to infinity, okay? It's a different kind of infinity, all right? So in this way, infinity works very much like any other number, regular number, okay? So it's different kind of infinity, all right? So, oh, Yeah, I mean, in a sense, yeah, infinity plus 1 is equal to infinity, right? So then what? Uh, let's see. So multiplication, we just found that they are not equal. Okay, 2 times infinity is not equal to just regular infinity. Okay, how about infinity plus 1? Um, okay. If you have something like x squared over x squared plus 2x, okay, so what's the limit of this? What you do is basically this. Traditionally in mathematics, this same as x go to infinity, you divide by x squared, okay? 1 over 1 over 2 over x. And if, when x goes to infinity, yeah, this guy becomes 0, you know? So this is 1, okay? 1 over 1, because this guy becomes 0. Yeah, that's traditional way of calculating the limit convergence, all right? And because convergence of a function, that's huge, huge in mathematics, okay? What if, how about, what's the value of this function when x is going to 0? If x is going to 0, 1 plus 2 over 0, 2 over 0 is infinity. So 1 over infinity is 0. So limit of, limit x is go to 0, this function, we could just call it fx, okay, is equal to 2 over 0 is infinity, okay? 1 plus infinity is infinity. 1 over infinity is infinity. 1 over infinity is 0, so that's 0, okay? Yeah. We want to define this infinity mathematics so that we don't have to go through all these intermediary steps, okay? So that's our goal, all right? I think what we can do is this. We just want to define infinity correctly, okay? And also 0 as well. Um, yeah, we can say infinity, okay, in terms of cardinality, the like Gero Cantor said, infinity is like variable like x, okay? Infinity plus number a plus minus a is equal to infinity. We can say that, okay? Um, or we can say 2 times, like a times, a say a is positive number, okay? A times infinity, uh, it's not equal to just infinity, okay? So like two times infinity is not equal to infinity, okay? So, and we can also say infinity squared plus infinity is equal to infinity squared. Is the law of absorption, okay? Yeah, law of absorption, okay? So here, infinity squared over infinity squared plus 2 times infinity, it get absorbed because infinity squared plus infinity is, it get absorbed, right? So infinity squared over infinity squared is equal to 1. Okay, so we just need to define infinity algebra correctly so that we don't have to go through this in intermediate steps. Okay, we are just trying to make some shorthand. Okay, that's all it is. So yeah, so a times infinity is not equal to infinity. Okay, so for example, what if you have 2 here? Okay, then you have 2 here. Infinity, yeah, it becomes 0. So this becomes 2, right? So yeah, 2 times infinity squared over infinity squared. So infinity squared, they cancel. It becomes 2. Okay? Because you multiply infinity by some constant, yeah, it doesn't get absorbed. All right? So that's that. Okay? Then it makes sense. Okay, so you're adding some number, constant number, yeah, it preserves the cardinality of infinity, okay, in Gero-Cantor's term. All right? Okay. And then in terms of x going to 0, we have to think about this in terms of x going to 0. We have to think about this like that's the inverse of infinity, okay, like 1 over infinity. Okay, that's then so that we don't have to come up with a brand new definition. Okay, we don't want to have just one single set of definition. Okay, so if x is going to 0, 2 times 1 over infinity squared, 1 over infinity squared. Oh my goodness, it's not very convenient, is it? But that's kind of what we did. We have to divide by x squared, you know. Yeah, yeah. Let's take a look. Okay. 2 times 1 over infinity squared and 1 over infinity squared plus 2 times 1 over infinity. Okay. and you multiply infinity squared on either side, and it becomes 1 plus 2 times infinity and 2. Okay, so 2 times infinity, that's 2 infinity, okay, becomes 1 plus this one get absorbed, so 2 times infinity, 2, so it becomes 1 over infinity, right? Yeah, so that's 0 by definition, all right? Okay. Yeah, we just try to come up with a consistent system of definitions so that uh, it's more convenient for us. We don't have to write down this limit x go to infinity. It's too bulky. Okay, so we want to come up with good equation and good set of definitions so that it's a brand new algebra. Okay, infinity algebra. Okay, that's what we're trying to do. We're trying to help out mathematicians. All right, that's what we're doing. Okay, so yeah, that's what we are trying to do. Because Gauss-Cantor's transfinite number system is, some people did study that, but it's quite, it's not quite mainstream thing. All right, so he was not quite successful in that venture. Okay, it's calculation of infinity. All right, so obviously then there should be a reason, right? Uh, yeah, so it's kind of unfinished projects, so to speak. All right. So let's do something that he thought about doing but didn't quite finish. All right. Yeah. So this infinity calculus, infinity algebra. Okay. So that's what we're trying to do here. Okay. So yeah, we just want to make constant system that's consistent with this all this calculus, limit convergence. We just want to eliminate the intermediary steps and make it more convenient. Okay, that's all we are trying to do. All right. Yeah, that's all. We're just trying to make some shortcuts, but still preserving the equality. All right. So that's what we are trying to do by the set of definitions. Okay, infinite algebra. It comes from good old calculus. Okay, this convergence limit. Okay. Yeah, we want to make consistent. Okay. Yeah. Also, there is this theory in computer science. The big O notation, small O notation. The that's like it can calculate the speed of infinity. Like, is it exponential growth, this function, or is it linear? Is it quadratic, cubic, quartic, quintic, whatever? Okay. Yeah, that's which is very useful in terms of calculating the efficiency of an algorithm. Okay, is it n squared or is it n log n? Okay, yeah, it's very has some practical usefulness in computer science to calculate efficiency of an algorithm. Okay, so yeah, we'll take a break and we'll be back. Okay. Okay. Whew. You know, we said we would put this stress vector system at the back burner, but let's forget it. Okay, because, we don't want to let this ghost, this zombie project, to occupy this space. Okay, we don't want that. So we're gonna just erase all this. Okay. If ever we come back to this, we just start from scratch. Okay. So yeah, it's all recorded, so we can always revert back. Okay. All right. Okay. So yeah, it's not this calculation of infinity limit. Okay, it's not that obvious because something new. Infinity doesn't quite behave like any other numbers because it's not exactly constant. It's not exactly variable. It's kind of halfway in between. All right, that's what infinity is. It keeps on growing, and it's interesting with something new. All right. This infinitesimality, okay, it can apply to every single number in the world. Okay, so for example, zero point 0.9999 blah blah. In mathematics, we shorten this as a 0.9 dot. Okay, and mathematically this is calculated as 1. All right, because like 0.333 is equal to 0.3 dot. All right, and the way we calculate it is this is equal to you put number of dots. Okay, you put 9 there from okay, 0.3 is equal to what? 3 over 0.1. I'm sorry. Yeah, 1 over 3. Okay, so 0.9 dot is equal to 9 1. Okay, so that's how it's traditionally calculated. Okay, and it's not exactly correct. Okay, the way we calculate this isn't exactly correct. It's more like limit. Okay, limit. Okay, of 0.99, that is what's equal to 1. Okay, because they're not the same. Okay, it's a limit. Where is this going? Yeah, it's going to 1. Okay, so it's the limit of this guy. Okay, that is equal to 1. So this isn't exactly correct. So it's like approximation. Okay. Okay. Yeah. So here. Okay. So limit of 0.3333, that's what's equal to 1 over 3. Okay. Oh well. Wait a minute. No. Well. Yeah, it's tricky. Okay, so oh boy. Infinity is so tricky. Infinity is very tricky. All right, so probably that's why nobody got it right so far. Okay, we're just taking a shot at it because we like challenges. It's a very intractable problem. All right. Oh boy. Well, the point I'm trying to make is this, okay? One, it could be 1.01, 1.0001, 1.00001. Okay, so every single number have this concept of infinitesimality, okay, attached to it. Okay, that's all the point I'm trying to make. Okay, it's not just zero, like 0.01, 0.0001. Okay, yeah, it's not just zero. They have this infinitesimality. Okay, one also has infinitesimality component attached to it. Okay, one plus 1.01, 1.0001, 1.0001, or two, yeah, 1.9, 1.999, 1.99999, that kind of stuff. Okay, so we can talk about this infinitesimality. All right, so the point I'm trying to make is this. Okay, so zero is kind of this. We have to come up with a brand new notation. Okay, uh, both for infinity and zero. All right, so yeah, it's a brand new concept. All we need to do is make some new names, new notation. Just like Galois theory, it was so inscrutable, ununderstandable, okay, indecipherable, okay, uninterpretable. Galois theory. Yeah, I'm sure he had very bad handwriting, I think, and because he'll just write down all these concepts, and people, oh my goodness, what the hell is this? All right, but later on, some diligent, good student mathematicians, okay, professional mathematicians, they were students of Galois theory. They learned from Galois. What they did was they came up with new notation, new names, like field theory, group theory. So they came up with these containers. So you have cup, you have soda, you have a cup, and you have water, right? Yeah, different. They came up with that's what language is. All right. You have a noun, like orange, apple, all those different names like banana, cup, water. Yeah, all these names in language, like noun or any verb, preposition like at, to, in, or adverbs like outward, outside, off, on, up. Yeah, all this adjective like pretty, ugly, whatever. Okay, all these words, vocabulary, they are like cups that contains a concept. Okay, so yeah, that's what this second generation group theorists did after Galois. Okay, they came up with brand new cups in order to contain different concepts that Galois came up with, like field theory, group theory, ring theory. Okay, yeah, they just named new things, just like in the Book of Genesis. Galois is kind of like God. He created all these concepts, and second generation group theorists after Galois is like Adam. They just named all the different concepts that Galois created. So Galois is like God. Okay, second generation group theorists, abstract algebraists, they are like Adam, who named all these different animals that God created, that Galois created. Okay. All right. So yeah, we can have brand new notation. All right. So we keep it simple. Okay. So infinity. Okay. And zero. Right. I'm trying to make a notation convention that's the that would be most convenient for us. We want to make as if we're going to make some changes, we want it to be backward compatible. Okay, so that we don't have to rewrite every single mathematics books because they'll be inefficient. Okay, we want to make a notation convention so that it's backward compatible. That requires as little change as possible. Okay, because we want to save some energy and efforts, time. Okay, so yeah, because like 1.001, like 1.00001, we're gonna notate that as 1 plus 0, something like that. Okay, so and which is not equal to 1. Okay, so okay, um okay. Well, in calculus you have L'Hopital's rule. I mean, I don't know what language is that from. It's kind of Los Hospital rule, L'Hospital rule, whatever. Low Hospital rule. Somehow they pronounce it as L'Hopital. I have no idea what. I don't know what language is that from. Okay, what name? Is it probably is French or something? I don't know. So like limit of f over g is x go to infinity or 0, okay, is equal to f limit of f prime g prime. Okay, so that's it's very convenient uh, mathematical equality, L'Hopital's rule. Okay, um, and we're trying to make some shortcuts. Okay, that's what we're trying to do by defining this infinity algebra. Okay, so that's what we're trying to do. Set of rules. Okay, set of axioms. All right, brand new number system. Okay, so Well, we can have zero circle and infinity circle. Okay. Um, what is this? We can think of this as a set of all different kinds of infinity. Okay. Because you have what? Infinity circle is set of all kinds of infinity. Infinity, two times of infinity, infinity squared, square root of infinity, logarithm of infinity, 2 to the infinity, blah blah blah. Okay? Set of all infinities. Okay? Zero is zero circle is defined as set of all zeros. We have 1 over infinity, 1 over 2 times infinity, minus 1 over infinity squared, 1 over logarithm of infinity, 1 over 3 to the infinity. Okay? Yeah. Set of all zeros. Okay? That's what I'm trying to tell you. Okay? Yeah, it's just inverse of that. Okay, so which is equal to 1 over infinity circle. Yeah, it's a notation. Okay, so notation convention. Okay. You just 1 over all this guy. 1 over all these guys. Okay, then you have through this distributive law, kind of, okay, then it gets inside of this comma, 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 so 1 over infinity, comma, 1 over 2 times infinity, blah, 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 okay? And I put negative here because, you know, they'll, yeah, as you can see, union minus 1 over infinity circle. Okay, so that's this, because if you multiply by minus 1, yeah, plus infinity, minus infinity, that's different, right? They're not the same. But in terms of 0, if you go 1 over, yeah, then they'll both become 0. Okay, it approaches 0. Okay, so this is not the same as the true 0. Like 0 apples, no apple, 0 bananas. Oh, I ran out of bananas. It's not like I have 0.11, 0.001 bananas. No, I don't have any banana, period. Okay. Yeah, I mean, I ate banana yesterday, so yeah, it's part of my body has some contents of banana that I ate yesterday. And I banana peel in the trash can, but we don't say, oh yeah, so I have 0.001 banana in my house. Banana became part of me, or I banana peel in the trash. Okay, yeah, there are some true 0. All right. It's a joke, okay? So let's say you're a girl, all right? I have no bananas. Oh, but hey, you're my girlfriend, so I ate banana like a month ago. So part of banana that I ate a month ago, it became probably my sperm, and I had sex with you last night. So yeah, in your vagina, you probably had some trace of the banana that I ate 1 month ago, because you probably have some sperm in your vagina. Just a joke. I don't get to have sex, so at least let me fantasize about it. Just kidding. Okay. All right. Okay. So we'll take a break, okay, and we get back to this. It's interesting, isn't it? It's kind of fresh. Yeah, we'll be back. Okay. So like when Gary Cantor came up with this concept of you know transfinite numbers, whatever. Okay, Aleph, whatever. Yeah, many mathematicians vehemently resisted that theory, and it upset a lot of mathematicians, famous ones like Kronecker or Poincaré, some philosophers like Wittgenstein, and yeah, they all vehemently criticized Gary Cantor's transfinite number system. Okay, so uh, that's kind of interesting. I mean, why did they have to hate that theory so much? Possibly because um, they hate Christianity. Okay, like science and Christianity, they have I mean, science and religion. They have some bad blood going on between them. Okay, science, religion, they tend to fight each other, right? Back in the days in Europe, they persecuted Galileo Galilei, Copernicus. Okay, so and Charles Darwin. Yeah, churches, European churches, they have some bad blood feud, family feud between science and religion. They hate each other, right? I mean, look no further than Jesus. Oh yeah, I'm Mr. Jesus. I can walk on the water. I can raise the dead. Okay, so it's oh, I'm Mr. Jesus. I can defy science. And Jesus didn't Jesus did not teach us a single mathematical equation. And he calls himself the Son of God. Okay, Mr. Jesus, well, so what do you know about mathematics, science, physics? You call yourself Son of God, the teacher of humanity. What equation do you know? Mr. Carpenter's son, do you know any mathematics? Okay, so yeah, science and religion, they hate each other. Okay, they fight each other. Because when Georg Cantor came up with this system of transfinite numbers, it's like mathematics of infinity. Okay, so he said, "Oh yeah, this is something that God told me to do." Okay, that was his explanation. So it's like the mathematics of God, the infinity. So perhaps that's why all these mathematicians resist that, because they hate religion, they hate Christianity. That's one explanation. Why did they have to get so upset? I mean, if you don't like this theory, then just don't learn it. Why do you have to attack it so, criticize it so vehemently with such a great hatred? Uh, Probably because they hate religion, they hate Christianity. Okay, because that would be my guess. Okay, so they got so emotional, you know. Whatever. It was interesting history to read about. I'm gonna turn on the heater. It's a little bit chilly. Okay. So, um, I guess I have to resort to this calculus book. Okay, so convergence, whatever, L'Hopital's rule, L'Hopital's theorem, whatever. Let's go to index. Limit of a function. Yeah, I really like this book. It has many colorful pictures. Picture of Alaska salmons. That's fun. It's a used book, so it has this hair. Eeh. This book. Oh, disgusting. Okay. Limit of a function. Okay, okay, okay. Okay, limit of a function. All right. Oh boy. So basically, what we are trying to do is here. I mean, what we are trying to do is this. Okay. Um, limit x approach to 1 of x is equal to 1, right? Okay. Limit if x approaches 2, 1 over x is equal to 1 over 2. Okay. But how about limit x approaches to infinity 1 over x? Okay. We want to write this as, well, it's 0, right? So you just plug in the number basically. We want to define this infinity, okay? We want to come up with a very nice definition that will be useful to us, okay? So just like we define I as square root of minus 1, okay? So that's the definition of I, imaginary number, all right? Just like this, we can define our brand new number, infinity, as 1 over 0, okay? That could be our definition of this. I'm sorry, circle. You know what? You remember the infinity set? Let's call it square infinity, okay? Because I want to circle things, okay? So yeah, let's call that set of infinity as square infinity, okay? Infinity square. Because I want to be able to circle things, okay? Or infinity underline, whatever, okay? So yeah, infinity is, we can define infinity as, so that's definition. Infinity is defined as 1 over 0, okay? Yeah, we can define it. So like, so this is, we just plug in the number, so 1 over infinity, and by definition this is equal to 0. We can do something like this, okay? And yeah, okay. Yeah, we want to come up with some system set of axioms that's fully backward compatible, all right? um okay. Mm. Okay, that's smart. So yeah, this guy's smart. So instead of you saying plus zero, they say zero plus to denote that it's like 0.00001. You know, yeah, that's zero plus. Yeah, instead of plus one is just one. Yeah, they use like something. We can use something one plus to denote that it's like 1.00001. Okay, if it is 0.99999 something, then we can use one minus instead of minus one. Okay, yeah, that's smart. Okay, good notation. Yeah, they have this epsilon delta whatever. I don't like that epsilon delta stuff. Yeah, I just skip that. Yeah, L'Hopital's theorem, L'Hopital's rule. That's very useful and powerful stuff. Yeah. Mm, I guess epsilon delta is not too bad. Whatever. It's kind of pretty. Yeah. Pretty pictures. There's L'Hopital's rule. I'm just reading this book. Mathematics. Kind of window shopping. L'Hopital. L'Hospital. El Hospital. 306. Yeah, L'Hopital. I mean, it's just different spelling of his name. Okay, but he's Frenchman, and in French, they tend to make the last consonant of a noun, of a word. Yeah, they tend to make it silent, the last consonant. But in the middle of a word, it's typically not silent. So l'hospital, l'hospita, whatever. Okay, yeah. But they spell his name differently. Sometimes they omit S. That's why we call it just l'hopital. Oh, okay. Yeah, L'Hopital's rule is something extremely powerful. Okay, I told you what it is, right? Yeah, it's something extremely powerful because you can just break down a function like by differentiating it, right? You break it down. Differentiation is like making kind of taming a function. It's like making kind of weakening the function. You make it smaller, smaller, lower, lower degree. Yeah, that's what differentiation is. Okay, and L'Hopital's rule. Yeah, you break down a function by differentiating it again, again, and again, so that you can find this limit. Okay, to see whether it's convergent or divergent, whatever. Is very very powerful kind of method. Okay, they have very interesting example here, L'Hopital's rule. Okay, so let's go over this. Okay, yeah, they somehow proved this L'Hopital's rule. All right, so it's this. Okay, so to simplify, limit of f over g is equal to limit of f prime over g prime. Okay, you can go on and on. You can just differentiate, break down a function, and so limit x go to 0, sine x over x is equal to what? Differentiate this, yeah, cosine x, limit of cosine x over 1, right? When x go to 0, yeah, this is 1, right? So, yeah, they're equal when x is 0, okay? Yeah, which is very, very interesting. And you have in this textbook limit of ln logarithm, log natural, ln x over square root of x when x go to infinity, okay? Infinity is equal to what? 1 over x over um, 1 over 2 times square root of x, which is equal to, you multiply by, so it becomes 2, I mean limit of, uh, yeah, you just multiply by square root x, uh, yeah, x and x, it kind of cancels each other, right? Square root, so limit of square root x 2 over, okay? So this becomes 0. So, when x goes to infinity. What this means is that ln x, okay, and square root of x, yeah, it's very good thing that they did here. So, square root of x function goes like this, okay? It's like parabola, okay? Parabola. Kind of, this is square root of x, okay? It's parabola that is lying down, okay? That's what square root of x is, okay? It's a mirror image over y is equal to x, okay? To that y is equal to x squared, okay? You swipe mirror reflection of against this y is equal to x, this straight line, that's square root of x, okay? So, yeah, well, I'm going fast, but yeah, please catch up, all right? Reflection of a function, okay? Yeah, you switch y and x, okay? Okay, y is equal to x squared, that's parabola, right? You switch the y and x, so x is equal to y squared. That's a mirror image of this line, okay? So you have parabola, then you have y is equal to square root of x, okay? That's what it is, okay? Anyway, and logarithm x is mirror reflection of y to the ex, okay? Y is equal to e to the x. So y is equal to e to the x goes like this, right? E to the x, all right? Y is equal to e to the x. The mirror reflection of that is like something like this, okay? So logarithm exponential function grow very quickly, okay? And but this logarithm function y is equal to ln x, okay? Log natural. It's grow very, very, very slowly, okay? It grows as slowly as exponential function grows very fast, okay? So growth of exponential function is very, very fast, right? So mirror reflection of that is a function that grows very, very slowly, okay? So yeah, it grows so slowly because its mirror reflection kind of anti-matter of that, it grows very, very fast, okay? So that's what it is. All right, so here this becomes 0, meaning we have some smaller thing over a big thing, okay? So meaning ln x, it grows so slowly, it grows even slower than this square root of x, okay? It's analogous as like the mirror reflection of this is e to the x, right? How about mirror reflection of this guy? X squared, okay? So we can see it this way, okay? Limit of ln x over square root of x is a brand new theorem, okay? This has to be the same as limit e to the x over, x squared over e to the x. It has to be, okay? We are inversing a function, okay, by ln x and e to the x. They are inverse to each other. You have function f and you have inverse function, right? In mathematics, okay? Yeah. So inverse function of ln x is e to the x. Okay, so we are inversing that, and we change upstairs downstairs. Okay, because square root of x is growing very slowly because its mirror image x to the x squared is growing very fast. Okay, so this has to be equal limit. Okay, how do you prove it? I'll leave it up to you. Okay, because intuitively this has to be correct. Okay, so to generalize as an equation, limit of f over g, it has to equal to limit of f inverse g inverse. Yeah, it has to be true. Okay, I'll let you prove it, or we'll let somebody else prove it. Okay, because life is short. I already made contribution to mathematics by coming up with this nice intuitive equation, brand new theorem. All right, we already made a contribution by coming up with it. Whether you prove it, disprove it, or kind of refine it, I leave it up to you or some other people. Okay, because I did my share of work. Okay, division of labor. All right, so yeah, we'll take a break and we keep doing this wonderful mathematics. Okay, mathematics for Sunday evening. Very fun. Neat. I'm gonna take a picture of this. Okay. Yeah, very neat. All right. Okay. I gotta go to bathroom, okay, real quick. So I'll be right back. Nature call. All right, we're back. Let's explore this concept of inverse function. Okay. Uh, well, we'll talk about infinity algebra. Well, maybe we'll get back to that later. All right. Let's just have fun. Okay, we don't have fixed agenda here. We just wander about. We're kind of wanderlust kind of people, nomad, traveling salesman, whatever. Okay. We do whatever we want. This is not a school. This is just us geeks, nerds, having fun with mathematics. That's all. That's what is. Life is short. Okay, so why not serious all the time? Okay, so I'm gonna drink a little bit. Okay. Yeah. Why serious all the time? Okay, what do I drink? Alright, let's have some rose hips and cranberries. Alright, so inverse function and this reflection, okay? I kind of gloss over it, but you know what? Let's go over it, okay? Instead of glossing over it, okay? Because it is important. It's good education. And composite composite function too. We'll go all over it, okay? So f, this is composite function concept. This is inverse function. What is inverse function? Definition of inverse function is you have to use this composite function concept. This is equal to identity function I. Okay. What is the identity function? Is y is equal to x. Okay. So this is like algebra of functions. We are treating function as if they are numbers. Algebra of functions. Okay. It's like this circle, the composite function. It's kind of like multiplication. Okay, this identity function is like 1. So like 3 times 1 over 3 is equal to 1, right? So it's kind of behave like that. Okay. So you have parabola, right? Y is equal to x squared. Okay. How do you find inverse function of that? It's very easy. You switch x and y. Now you have inverse function, which is, this is like x is equal to y squared. So y is equal to plus minus square root of x. Okay, plus square root of x minus square root of x. Okay, is the mirror image along y is equal to x. Okay, that's what inverse function is about. All right. Okay. So yeah, let's apply our brand new, we call it, we can call it like inverse L'Hopital's rule, whatever, or L'Hopital's rule 2. Okay, second law of L'Hopital, whatever. But L'Hopital theorem, what I just read is it was discovered before by something like John Bernoulli or something. Okay, yeah, Bernoulli equation. I'm not sure it's the same guy, but whatever. Okay, physicist, mathematician, whatever. They say he has also a brother who's also a mathematician, physicist. I don't know which one is which. Okay, whatever. So, limit of f over g is equal to limit of g inverse f inverse. Okay. So, let's see if this is any useful whatsoever. You have a what, ln x over square root of x, right? This should be equal to limit of e to the x squared. Okay. You differentiate, okay, and there is limit of 2x over e to the x, and you differentiate that again, well, limit of 2x over e to the x, which is equal to, running out of space, limit of 2 over e to the x. You differentiate it again, is with limit of 0 over e to the x, which is equal to 0. Okay? Yeah. Because e to the x, e to the infinity is equal to square notation, okay? Infinity square, okay? It's a kind of infinity, okay? And 1 over any kind of infinity, the e to the infinity or 2 times infinity, whatever, okay, is equal to a kind of 0. Okay, it could be 1 over infinity squared, whatever, okay. More correctly said, yeah, it belongs to this set of infinity. It belongs to a set of this 0 squared, okay, but for simplicity we just say it equal, okay. Okay, this set symbol, okay, belong to, is a member of, all right. So that's that. Yeah, now we have some very powerful tool here, because it's just easier to, many times it's easier to think in terms of this inverse function. Come on, because square root of x, to differentiate that, oh, take derivative of the square root of x, that's headache, man. No, we don't want to do that shit. So yeah, just make it upstairs and find this inverse function. Then you can differentiate using L'Hopital's rule. It's just a lot easier. Okay, so yeah. I have never seen any formula like this before. It's something very basic. It could be something new, or it could be have been discovered by someone else. We don't know. But I haven't seen this in any mathematics textbooks that I've ever studied or read. Okay? And it's very simple formula. probably it's not that difficult to prove this. Okay? We can take a shot at proving this. To prove this, you know what? We may need to study how L'Hopital's rule is proved. Okay, so let's study that. How did they prove L'Hopital's rule? I'm not sure if it is easy enough to be in this college calculus book. Not sure. So L'Hopital's rule proof. How did I prove L'Hopital's rule? Okay, they used Cauchy's mean value theorem. Okay, so that's how they used it. Uh, I'm not sure how to prove this. I'm not very good at proving. I mean, mathematical proof is something very beautiful. Okay, it's beautiful thing. Okay, but I'd rather leave it to someone else. Okay, because this what second L'Hopital's rule, inverse L'Hopital's rule, whatever, however you name it, is something very easy. Okay, yeah, it's not fancy calculus. No, it's just inverse function. So if it's already there, if it's already proven or discovered before, it should be in this book or any college level calculus book because something very simple. Okay. Is it correct? Incorrect? I don't know. My conjecture, my speculation is that it has to be true. Okay. But maybe it's not correct. maybe you have to qualify it a little bit because L'Hopital's rule is there's also qualification. It has to be 0 over 0, infinity over infinity kind of type of relationship. Then L'Hopital's rule is correct. Maybe there's some qualification like that. All right, so necessary and sufficient condition so that this equation is true, or maybe it's true for any function. I don't know. Okay. You can probably one way to go about proving this is like you kind of multiply x y's or composite x y's. Here you multiply, here you multiply, composite function, and it becomes identity on either side. I don't know. Okay, I'm just giving you some clues how to go about it because I don't want to prove this. Okay, it just makes sense this way. Okay, so in my opinion, it's a conjecture. Okay, go ahead and prove it. I don't think it will be too difficult to prove this. All right. Yeah, L'Hopital's rule. Yeah, I just skimmed over how they proved it. Using what Cauchy's mean value theorem. Yeah, I understand how they proved it. Okay, but it's not very difficult to prove L'Hopital's rule, and it's a very powerful equation, and it's very easy equation. So if it's been already discovered, probably it should be in the calculus book, college level calculus book, but it's not there. Okay, so two possibilities. Either this is not correct equation, or this is correct equation, but it's been never discovered. Okay? All right? Yeah. But I think it is correct. All right. Yeah. Okay. Yeah, you will discover something new, possibly, potentially, if this is true. We're just too lazy to prove this. Why don't you do it? Well, let somebody else do it, okay? Because I don't want to prove this. All right, I did my job, okay? To come up with this, it wasn't easy. It took some labor. My foregone Sunday evening, okay? Yeah. Because if you just go straightly applying L'Hopital's rule here, oh, come on. It's to differentiate square root of x. Oh, it's nightmare. I mean, it's not too hard, but we would rather differentiate x squared. It's just easier to differentiate that. Yeah, ln x, it become differentiate of that 1 over x and differentiate of that, and come on. We rather differentiate e to the x because differentiation of e to the x, derivative is e to the x is always the same. It's a lot easier to differentiate e to the x again and again and again because it's still the same, e to the x. Okay. And to differentiate polynomial like x to the second, x to the third, it's a lot easier, okay? Because it eventually boils down to a constant or even 0. Okay, it's a lot easier to differentiate that. Because limit of this using L'Hopital rule again and again, yeah, we know where it's going, 0. Okay? But differentiate this guy again and again and again, my goodness, 1 over x, then 1 minus 1 over x squared. No, we don't want to do that shit. No. No. Okay. What is okay, 1 over x, differentiate that, minus 1 over x squared, differentiate that. What? 2 over x to the third. One over x prime is equal to what? Minus 1 go, so minus 1 over x squared. Okay, so minus 1 over x squared, you differentiate that, is what? Minus what? X to the minus 2, you differentiate that, and this becomes what? 2 over x to the third. Okay, 2 over x to the third, differentiate that. Is what? My goodness. Minus 3, okay. So minus 6 over x to the fourth. Yeah, it's not easy, okay? It's a mess. Alright, so yeah, we rather just differentiate the inverse function of that, okay? So x squared or x to the third, x cubed, x fourth. Yeah, we know where it's going. You differentiate again. It all boils down to 0. Okay? E to the x, you differentiate again. We know where it's going. E to the x. Okay? We rather differentiate the inverse function of that. Okay? So I think this is correct. But to prove this, I don't know how to prove this. Okay? It should not be very difficult. Probably if you don't even have to measure in mathematics to prove this. If you have taken like 3 semesters worth of calculus in a 4-year universities, probably you'll be able to calculate this. I mean, prove this or disprove it. Okay, I don't know if that is correct or not. It's conjecture. Okay, in mathematics, people make conjectures. It's either they're too lazy to prove it, or maybe they tried but they failed to prove it. Okay, in our case, our excuse of not even trying to prove this is that life is short. Okay, we already made contribution. Yeah, this division of labor. Okay, come on, I don't have to do everything. Come on, there are plenty of people in the world who have taken 3 semesters worth of calculus in 4-year colleges. I'm just one of them, and I did my job as coming up with this, and it was not that easy. It took a lot of labor. So why should I do all the work when there are so many people, even mathematicians or mathematics majors out there, or any people who have taken like 3 semester worth of calculus in college? Yeah, let's give them work. Delegate. I'm just one person. You may think, okay, you are making all these bullshit excuses. Why don't you use your energy to prove this instead of wasting energy and time making excuses not to prove it? Why don't you use the same energy to prove it instead of using the energy of making excuses not to prove it? Yeah, you may say that, but my self-defense. Okay, so you accuse me of not proving this, using energy, try to persuade you convince you that it's okay that I don't prove this. It's because because I want to take a break from mathematics. So I'm making this lawyer's excuse. I'm a lawyer on paper, so it's more fun to take break from mathematics, and now I'm in this jurisprudence, law, study of law, the art of defense lawyers. Mathematics is fun, okay, but we're kind of tired of it. So I want to take a break from mathematics. So yeah, let's do some defense law, you know, lawyering, making excuses. Because I told you this many times. All you learn in law school is how to make complaints and how to make excuses. That's all. The one and only thing that's the two things that you learn in law school. Okay, you learn how to make complaints and you know how to make excuses. That's the that's the only two things you learn in law school. Okay, so people love that joke. We're gonna take a break. Okay, so then we get back to. Okay, but I don't want to prove this. Okay, come on. It's division of labor. Why do I have to do everything? Why don't you do something, huh? Delegation, okay? Okay, we're back. So yeah, it shouldn't be too hard to uh, prove this. Okay. The intuitive way to think about it is this. Boy, uh, we are in the realm of this infinity algebra. Okay, the Gero Cantor, he took a shot at it. Okay, and before that, I mean, why are we in infinity algebra? Because we want to generalize number system. All right, we want to define brand new numbers. Okay, and we want to find out the relationship between number system, expanding universe of number systems, and expanding universe of operators. Okay, because mathematics is all about generalization. Okay, so that led us to defining 1/0, just like definition of I, you know, imaginary number. Okay, yeah, I squared is equal to -1. Okay, I is equal to positive square root of -1. Yeah, it turned out to be a very powerful and useful definition in mathematics. Okay, so we are trying to contribute to mathematics. Okay, you can call it humanological mathematics, whatever, mathematical humanology, whatever. Okay, so yeah, we are putting mathematics on a spotlight, limelight, on the center stage. Okay, so as humanologists, we are contributing to mathematics. Okay, so yeah, it's humanological mathematics, not mathematical humanology. Okay, we are not dealing with human phenomena here. We're dealing with mathematics only. Okay, it just happened that we happen to be humanologists. Okay. Uh, Give me 1 second. I'm just talking to my friends. Okay, so um, so in computer science, there's this big O notation, small O notation. Yeah, we typically use big O notation. Small O notation, well, we don't use it very often, but okay. Let me turn on the hero. Okay. And it's very powerful tool, big O notation tool. Because you have algorithm like sorting algorithm, whatever algorithm there may be. Okay. There's algorithm about traveling salesman, shortest finding the shortest path in a graph. You know. Yeah, I major in computer science, so I learned. I know what it is. Okay. It is very fascinating stuff. Big O notation. Okay, O, order of magnitude, whatever, order of growth of a function. Yeah. So in computer programming, you have inputs. Okay, so input is like a variable of a function. Okay, output is like dependent variable. Input is like independent variable. Okay, so as the input grows, what will be the output? What would be the time it takes to calculate this algorithm? Mathematical algorithm is can be programming algorithm of computer program can be thought as a function, mathematical function. Okay, in computer programming language, lingos, jargons, terminologies, yeah, they use function. Okay, it's a function or subroutine. Okay, yeah, action. You take input, so some interactive website. Okay, you click a button. There are many buttons, right? That's the input. Or you type in some numbers or text. Then there's some output, right? So yeah, for example, calculator. Okay, it takes some inputs. A calculator online or in your computer, or as a physical calculator, scientific calculator, or accountant's calculator, whatever. Yeah, there are inputs. What are inputs? Numbers and operators. What is 2 plus 3 equals? Those are the inputs. You have 2 plus 3 equals. Those are 4 inputs. Output 5. That's the output. Okay. So it's a function. Okay. Any calculator which is computer programming. Okay. Yeah, that's the function. You have take input and you give out outputs. Okay. Or whether you have some app in your cell phone. Okay. What are inputs? Yeah. What's the weather in Las Vegas, Nevada next Tuesday? Okay. What are inputs? Yeah. Space and time. Space input and time input. Okay. Yeah. Weather of where and what time? Yeah. Las Vegas, Nevada next Tuesday. Okay. Spatial input and temporal input. Okay. Output, yeah, it's gonna rain. It's gonna be 80 degrees. Okay. Yeah, in terms of humidity, the time of sunrise, humidity, rain or shine, or temperature, yeah, dew point, whatever. Okay. Yeah, so those are the output sets. So set of inputs, set of outputs. Okay, that's what function does in computer programming. In mathematics, same way. Okay. Okay. All right. Let's go back to this infinity algebra. Give me 1 second. Talking to my friends. Okay. We have like 1 hour left. Okay, so we may still continue after this episode. Yeah, it doesn't matter. Uh, so infinity mathematics. Okay, so when Gero Cantor, his transfinite number theory. Okay, he, I mean, I just gleaned over it, just scratching on the surface. I read about it, transfinite number. Okay, in Wikipedia. Okay, so yeah, I kind of got the idea. Okay, what he was trying to achieve by this transfinite number theory. Yeah, so cardinality, ordinality, whatever. Okay, so yeah, infinity. Okay, they're not all the same. They're different kinds of infinity. Okay, so it's a brand new algebra, brand new number system. Okay, it will have its axioms, set of rules, then theorems. Okay, it's just something new. Okay, so whenever something new comes about, yeah, people have this fear, fear of something new. We can call it neophobia, fear of something new. Yeah, they because they rather err on the side of caution, on the side of caution, safety, because if there's this brand new this space alien coming towards Earth, we're not sure. Do they are they nice or are they bad? Why did they come here? Probably they came here to steal from us, or maybe they came here to trade. Maybe they will give us something and we give them something, or maybe they came here to just to invade us, to steal from us. We are not sure. So let's err on the side of caution. So let's just shoot the arrow to the. I shot the arrow in the sky. It's Twilight Zone episodes, okay? Multiple of them. Yeah, let's nuke that bitch in the sky. Let's bomb it. Let's kill it. Because we are not sure did they came to steal from us or trade with us. But we are doing just fine without them. So let's err on the side of caution, so let's kill it. The fear of unknown. Fear of unknown. Okay? So difference. If somebody's different from you, like xenophobia, yeah, because it kind of bothers us. Why is he so different from me? It's annoying. So let's pick on him, bully him. Let's bully the shit out of his ass. Okay. And so yeah, he's a minority. You know. Why is he so different? Let's pick on him. We don't want him. Get the fuck out of here. Get out of here, man. But some other people would be, he's so different from me. So yeah, it's exciting, entertaining because he's so different. It's entertaining, amusing, shocking sometimes, but yeah, it's something different. It's entertaining. Okay? So if somebody's so different and brand new, there are two reactions. I hate him or I love him. It's either you hate him or you love him. Okay? It's like President Trump, right? Or Mr. Donald J. Trump. It's either you hate him or you love him. Okay? Because he's so different. Okay? Or whatever. Lady Gaga. Either you hate her or love her. Okay? Gayism. Homosexuality. Yeah, you hate it or love it. Okay? Because something new. It could be good new or bad new. Okay? If somebody come up and say, let's legalize murder. Let's legalize theft. Okay? That would be bad new. It's something new, but it's bad. Right? So, yeah, if something is new, we didn't have enough time to think it through. we didn't have time to analyze whether it's right or wrong. Okay. So give me a minute, okay? Just don't push it on us. Give me some time to think it through. Is it right or wrong? This brand new thing. So yeah, just slow it down, baby. Slow it down. I'm not quite sure if you're right or wrong. It's something new, so I need some time. Don't shove it to our throat. Don't shove it to my mouth. Give me some time. Let me think. Where do you see it most often, most commonly? Romance market. Okay. Oh, lady, you're so beautiful. Yeah, you're new to me, but I know instantly because I'm biological being by evolutionary process. Yeah, I'm programmed to perceive this beauty. You, young, slender, tattoo-free, piercing-free. Yeah, yeah. I want to have sex with you, baby. Yeah, I'm a man and you're a girl, beautiful, young, slender girl. No tattoo, no piercing. So yeah, I want to have sex with you. May I? And she's like, oh, hey. Oh, hey, slow it down, baby. I don't know you yet. So you wanna come inside of my vagina? You wanna get me pregnant? But I'm not sure if you have good gene or bad gene. You're an unknown. I wanna err on the side of caution. So no, fuck no. You're too pushy, rushing, pressure. No, I wanna be free and independent. So answer is no. Bye. Bye. Okay. Give me some time to think about this, okay? Should I go out with you or not? Because I'm not sure if you have good genes or bad genes. Are you a good person or a bad person? I don't know. Okay, so okay, this is funny. We'll take a break, okay, and we'll continue. All right. We're just having fun, okay? So, all right. We'll take a break. Okay. All right, we are back. Where's my glasses? Is it here or oh, it's out there? Okay. So infinity calculus, infinity algebra. All right, it's like this. It's about function. Okay, the growth of a function because we do two-dimensional coordinate. Okay. All right. You have y is equal to x. That goes like this. Y is equal to x. Okay. And then you have y is equal to 2x. Y is equal to 2x. Okay. Y x. Okay. And then you have y is equal to x squared. Okay. Yeah, y is equal to x squared. It was lower than y is equal to x or y is equal to 2x. But eventually it catches up and it exceeds. Okay? Like late bloomer. Okay? And not only that, you have this y is equal to 2 to the x. Y is equal to 2 to the x. Okay? Yeah, it's slow at in the beginning, but eventually it's bigger than any polynomials. So limit x go to infinity, okay, of x to the n a to the x when a is more than 1, okay, it's always infinity, okay, because meaning a to the x a to the yeah, a is more than 1, okay, like 2, 3, 4, 5, whatever, 1.1, 1.111, 1.0001. If a is more than 1, okay, a to the x in the eventually it's always more than x to the nth, okay. To prove this, it's easy. It's a L'Hopital's rule. Okay, you derive. Okay, take derivative. This guy always become what? It becomes 0. If you differentiate. Okay, it becomes 0. This guy is log n times a to the x, log n squared a to the x, log ln a. I'm sorry, ln a times a to the x, ln a squared a to the x. Yeah, it's constant times a to the x. Okay, so yeah, it becomes, meaning yeah, a to the x exponential function eventually, yeah, it's like a to the infinity is bigger than infinity to the n. Okay. It's very well known thing in mathematics. Okay, if you don't understand this, yeah, catch up. All right. Yeah, L'Hopital's rule is polynomial. Well, it's like polynomial. Okay. Polynomial is like x squared, x cubed, blah 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 blah. Okay. But exponential function is like 2 to the x, 3 to the, 3 to the x, 4 to the x, okay? That's exponential function. Okay. We are just switching the order. We have x to the first, x to the second. We are switching the order. Okay. 1 to the x, well, that's always 1, right? But if x is this guy, go downstairs and upstairs, all right? It makes a huge difference, okay? So we are talking about the power operator, all right? We are just switching the order upstairs or downstairs, okay? Yeah, power operator, okay? These guys are always bigger than this guy. Polynomial and exponential function. Because polynomials, they grow geometrically. How about this? 1 times x, 2 times x, 3 times x, okay? And here you have this plus to the first. Here you have plus to the second, which is multiplication. X times x, x times x times x. Here, x plus x, x plus x plus x. Here is a power operation, okay? Plus to the third, which is equal to this power operator, okay? It's like, okay? Whatever, okay? So yeah, it's this bigger order of magnitude, all right? Before this, it's plus to the zeros, or yeah, maybe x plus 1, x plus 2, x plus 3, okay? X plus n. Here, x times n. Here, x to the n. Nth. Here, whatever. I don't know. Okay? Exponential function, whatever, okay? I think these two guys are kind of, it's not the next order, but we are just switching the two sides of this exponential operator, okay? We are relaxed, okay? We are not being mathematically rigorous here, okay? But you got the idea, all right? So, okay? You got it? Because we're gonna erase it, all right? Yeah, let's take a picture, okay? We are relaxed, all right? Let's take a picture. Ugh. Okay. Now we can erase it. It's kind of getting hot, so I'm gonna turn off the heater. Sorry to bother you like this. And we no longer need this calculus book textbook, so I'm gonna put it back in the shelf right here because I'm hitting it every time I'm walking. This piece of hair, oh, I don't like hair hanging around like this. So annoying. Textbook on the floor. Oh, I'm shedding so many hair, man. That's why I don't have any pets, because me as a human being, as Homo sapiens, I myself is shedding enough hair, okay? If I have a pet, oh my goodness, what do we do? What do I do with all this hair on the floor and the food? My goodness, I don't want to eat some dog hair in the breakfast. Would you like dog hair in your breakfast? My goodness, no. Hell no. Fuck no. Okay. I'm shedding enough hair myself, okay? I'm losing hair everywhere, okay? So my nose hair, ear hair, pubic hair, pubic hair, on top of my head hair, whatever. Okay, I'm losing enough hair. Okay, so no pets. All right. Okay, so but gotta tell you this. You know, I eat chicken, right? Sometimes, like maybe once a year or 3 times a year, I eat this whole chicken with its skin. So there's this chicken hair on the chicken skin in this broiled chicken rotisserie. Okay. Or when I eat pig in Korean traditional dish, they have this pig skin. Okay, it's like, yeah, this what fried rind, pig skin in America, but in Korea they what they do is they smoke the pig skin. Okay, and there's some this very bristly, this tough chicken. I mean pig hair sticking out of this pig skin. We eat that. I mean, not too much, but every once in a while, yeah, it's there. We eat it still. Chicken hair, bristle, pig bristle, whatever. Yeah, sometimes we eat that. Okay. But no dog hair or cat hair. Okay. Ah, no, we don't want to eat that shit. No, no way. We're just taking a break from mathematics. Okay. So. Okay. Let's take a break. Oh boy. Let's take a break. Ah. Okay, we're back. All right. So infinity algebra. Okay, so well, let's start with the definition. All right. So the definition of infinity, like like definition of I is equal to square root of minus one. Okay, that's definition. All right, starting point. Okay, so definition of infinity is plus one over zero. Okay, or plus wait, zero, just zero. Okay, if we define that, okay, now the whole new world, brand new world opens up. Brand new number system. Okay, it's like there's this Disney movie, animation movie, Aladdin. Okay, something like that. Da da da, da 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 da. Oh, brand new world. Na 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 na. La da 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 la. Brand world with you. Oh, brand the whole new world. La la la. Something like that. I can show you the world. And that is I. Na na, tell me, princess. Na da da, na da da da. Oh, brand new, whole new world. Sounds like, yeah, Disney. Yeah, they made very great Disney songs. Okay, like there's this Disney animation movie about Hawaiian roller coaster. Hallelujah, dun 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 dun. There's no place rather be. Ocean blue. The sky horizon. Hawaiian roller coaster ride. Oh, it's a fantastic song. Well, this country song themed the cars in Disney movie. Three dimensional what this Pixar whatever. Okay. Da 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 da. I dare you all night long. Life's a highway. All night long. What a fantastic song. Or this Pocahontas, President Trump, he doesn't know. He doesn't appreciate this Disney animation movies. So. If I never knew you, na da da da. Yeah, it's fantastic song, Pocahontas. If I never you knew you. It's a great song. Yeah, fantastic. Yeah, I love this music video, Pocahontas. Who's it was African American girl and a Hispanic guy. Okay, they sang this song together. Oh, so beautifully done. Dun dun da da dun dun. Very urban setting, kind of ghetto urban. Yeah, Hispanic, African American, ghetto, kind of urban, inner city, ghetto, whatever. Yeah, it's very beautiful. This diversified music video. One of my favorite of all time. If I never knew you, na da 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 da. Close your eyes. If I never knew you. Yeah, na, 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 beautiful. Na, 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 na. Yeah. Oh, Little Mermaid. Yeah. What? Part of your world. How does the. Yeah. Well, Under the Sea. Yeah, sang by African American guy. And white girl. Duet. Under the sea. Nobody's gonna beat us. Break it, take it from me. And then part of your world, a brand new world. I think it's the same singer, white girl in California, a fantastic singer. Nowadays, it's all taken over by these lesbians. Lady Gaga, Katy Perry. Oh, this lesbian singing. Oh, it's like dykey, lesbianish, satanic, devilish, ugly as fuck, dude. Even Christian gospel singers, yeah, they do this dykey lesbian style. Satanic, devilish, so ugly as fuck. Oh my goodness. What happened to us? What happened to us, the US? Gayified, homosexualized. Come on. I mean, sing like a girl, dance like a girl sometimes. That's fine, okay? But a girl singing like a man or making muscle like a man, no, that's not pretty. It's ugly, okay? So if you are a woman, if you are over 50, yeah, you need to do weight training, okay? Because you're losing muscle weight, bone weight, yeah, you have to do weight training if you're over 50 or even 40, okay? That's fine. But young white, not white, any young girl of any race, they shouldn't do too much muscle weightlifting, okay? Because it's not pretty, all right? We want women to be womanly, we want men to be manly, okay? But falsetto voice like Bee Gees, sometimes Beatles, Beach Boys, yeah, it's so cool, okay? Whatever. So yeah, this is definition of this Möbius stripe. Okay, this infinity. Okay, so that's the definition. So, uh, now we're gonna go toward the next step, cardinality. Okay, so because not every infinity is the same thing. All right, so infinity plus some constant number a is equal to infinity, okay? But infinity multiplied by a's positive number for now, okay? Okay, a plus minus a, that's infinity plus minus a, that's equal to infinity. But infinity multiplied by a, given a is positive number, okay? It's bigger than infinity. They are not the same. Okay. Infinity to power a, infinity to the eighth, is bigger than infinity multiplied by a. Okay? It's like exponential function. It's always bigger than polynomials. Is that concept. Why? Because you have plus to the first, plus to the first, plus to the second, and plus to the third. Okay? You have different cardinality, different hierarchy, different echelon in this hierarchy. You have plus, multiplication, and you have power. Beyond that, yeah, we have more. Okay? It's generation of plus to the first, plus to the second, plus to the third, blah blah blah. Okay? It's that. That's the cardinality. Brand new cardinality. That yeah, Gary Cantor did. He took a shot at it, but he didn't quite get it. Okay, so it's like what? Poincaré, Wittgenstein, or Kronecker, if they opposed it, maybe it was healthy, constructive criticism, okay? Because he didn't quite get it right, okay? He said, "Oh yeah, oh it's from God. I'm Christian, so you have to just take it. Just take it. It's so good. It's so good. I'm prophet, mathematical prophet. So yeah, it has to be good. You know, just take it from me, because I'm from God." And Kronecker, Poincaré, Wittgenstein. No, 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 no. Stop, 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 just stop. You cannot gloss over like that. No, you're a human being, and we don't like Christianity. We are secular, you know. So secularism has some value because Christians sometimes, yeah, we are human beings. We make mistakes. Okay, we are not gods. I mean, even prophets. Yeah, they're human beings. King David, King Solomon, even Mr. Jesus. Yeah, they make mistakes. They're human beings. Okay, so yeah, so secular people, yeah, they make good, positive, constructive criticism against Christians, Muslims, Confucianists, Zoroastrianists, Buddhists. Yeah, it's all diversity. You know, we criticize each other. It's a refinement. Okay, no pain, no gain. All right, we are refining each other. Okay, all this diversity. All right, yeah, so good. Okay. Let's take a picture of this. It's kind of pretty. Yeah, I'm still talking to my friends. Just give me 1 second, okay? Talking to my friends. Yeah, just texting with my beloved friends, okay? Who take care of me and whatever. Yeah, just helping each other out, you know. Being good friend. Yeah. Okay. Okay, so yeah, we got this. Okay. There's infinity mathematics, infinity algebra, all right, and yeah, a is a positive number. Okay, so yeah. So what is infinity? Yeah, definition of infinity is equal to 1/0. That's the definition of infinity. Okay, so that's that. Okay, so yeah, because we want to simplify things. We are trying to help mathematicians. All right. Oh, it's so bulky to write down like limit x go to infinity 1/x or whatever. We're just trying to help you. All right. Okay. We're just trying to help you. That's all. So we have this cardinality, okay, this ranking echelon, okay, different degree of infinity, okay. So infinity, 2 times infinity, or infinity squared, infinity to like 2 to the infinity, they are not the same, okay. They're different hierarchy, all right. So yeah, we want to simplify this infinity calculation, all right. We want to come up with brand new algebra. They would make our life easier. Okay, that's all mathematics is about. Yeah, we want to make it easier, simpler. Okay, we want to be economical, efficient. That's what this was about. We have 2 minutes left, so let's stop here and we'll continue. Okay, thank you. I see you. I see you after 5 minutes. Okay, we'll take a break. Okay, we'll continue. Okay, okay. Because night is young. All right.